All right, this is a much shorter talk, and it's just some thoughts I have about checking your RMG built mechanisms and building good mechanisms in the first place. And I think other people in this room might know just as much about this as I do, so feel free to contribute. All right, just the concept is very important. What are we trying to do? When do we think an RMG model is good? An RMG model is good when this quantity omega, I'll define this in a second, is very close to the truth. There's a true value omega, which is a function that appears in the species conservation equation, and is what we call the rates of the reaction, the rates of the species being consumed by chemical reactions. In chemical engineering speak, we call it R, little r. Okay. In mechanical engineering speak, they call it omega. Okay. It's the chemical source term. It's how much the chemical species are changing because of chemical reactions. It's not counting the concentration of species change because they diffuse, they change because they conduct. We're not worried about that. We're worried about the fact that they also can react, and that's the reason why the chemical species change. This is the species conservation equation. If you want to see where this comes from, you look at textbooks like Key's textbook on chemical reacting flow. And basically, this is just conservation of species. So it says that the rate of change of the mole fractions is related to a convection term with the velocity of the flow, a diffusion term. If you have a gradient of the concentration, you'll get some diffusive flux, and chemical reactions, omega. Now the omegas are just what you expect. They're the rate coefficients times concentrations, and they have a forward direction and a reverse direction. For the reverse direction, we use the equilibrium constant to get the reverse direction. Now this one I wrote the whole thing out just to remind you. There's also something called activity coefficients. You might have heard of them once. That's because you could have non-ideal solutions, for example, and therefore the activity might not be equal to the concentration. Some complicated stuff like that. But basically, it's what you expect. And this omega, would go to 0 when all the reactions are equilibrated, because the reverse rates would be equal to the forward rates, and that's where the equilibrium constant comes in. And you can see I have the forward rate coefficient here and here, because the ratio of these two is the reverse rate coefficient. Okay. Now, when we make a chemical model, what we report is a list of the reactions, which is what's telling the stoichiometries, these n's, and we're telling the rate coefficient expressions, and we also give a thermophile that you can use to evaluate the Ks, and if we're really great, we also provide the activity coefficient model. Okay? And if we give all that information, we think we've told somebody everything they need to construct the rate file. Okay? That's our idea. At least in the case where the environmental effects are not that much of a deal. All right. So now we're trying to assess if RMG is giving us a good model. I would claim that it's giving a good model if the omega that it predicts is really close to the true omega that would actually be physically happening in the system. Now, what we have from, say, RMG, our model's omega, is different from the true omega by 2 terms. One term is because the rate coefficients and the thermochemistry and the activity coefficients that we have in our model are different than the true values. So the numbers in the model are not true, are not correct. Right? Even in the best model, they'll only be good to a certain number of significant figures. Right? And in our models, often might even be wrong in the first significant figure. Okay? What I call parameter error. It's that the model structure is right. We have all the reactions. Everything's fine. It's just our numbers are wrong. We have the wrong thermo. We have the wrong rate coefficients. And we just need to work on improving that. So that's one possible thing. But there's another part, is because we might have actually forgotten some of the species or some of the reactions. So our model that we write down does not include everything that's really happening. All the chemical reactions are really happening in the model. So I'm going to call that error the model truncation error. And that's just due to the fact that the true model has all of the species in it, but Our model does not. And in this way of writing it, this is represented by this matrix Z, and Z is a diagonal matrix, and it has 1s in the diagonal for all the reactions that RMG included, and 0s in the diagonal for all the other reactions in the universe. But the real model, the true model, has 1s for everything, because it includes every cosmic reaction that there is in the world. All right. So when we build a model with RMG, we're going to have both kinds of error, parameter error and model truncation error, but the strategy of how to deal with them are completely different. When you get a model, you will not know which of these errors is bigger than the other. And a key thing for you to figure out, or try to figure out, is which of these errors is really the problem, because their solution to them is completely different. Okay, so this is what RMG is doing roughly. And so this maybe should be very straightforward for you now after a couple days of this class, but maybe it's worthwhile to go through it. Okay, so RMG can make estimates of the K's and K equilibriums, as discussed previously by Matt. And it has recipes that allow it to create reactions, or basically reaction templates. And the main RMG algorithm is really trying to reduce the model truncation error. So what it's saying is we have some list of current species in the core and some species in the edge, and we're trying to assess if any of the edge species are so important that we have to put them into the core. So we somehow have estimated what the rates are, and from that estimate, we can estimate that some edge species is formed at a high rate, and therefore it must be important, and therefore we're going to put it, RMG is going to move it from the edge into the core. That's the main operation. When it does that, it moves all the reactions involving this edge species X, like this and like this, into the core. And then it generates all the unimolecular reactions of X and adds them to the list. And then it estimates the concentrations of the core species by solving dc dt equals the current estimate of omega, which now includes X as additional. So we've added additional reactions, additional species. This formula is now different. It now has one more species because it has X as an extra species than it did compared to the previous iteration. And the omega is different because it involves the reactions of X. And then we go through the all the different possible reactions, bimolecular reactions, which have not been considered yet, and see if originally we decided they were so slow they didn't matter, but now because we have a different estimate of the concentrations and a different estimate of the omegas, therefore some of the bimolecular reactions we thought were negligible before might now be important. So we test and we add those reactions, and then we reevaluate the omega, including all these new reactions we just generated, and we go back and do the same thing, iterate. And the whole purpose of this entire thing is not to improve the parameter values, because we didn't do anything to improve them, we just dumped them in. This is all about trying to reduce the model truncation error by adding more and more reactions in. So we're turning some of the zeros in that huge matrix Z, were zeros before we're turning them to ones. We're trying to add some more, and then that's going to reduce the truncation error. Because the more, when Z goes to the identity matrix, then these two, or the model truncation error will be 0. You have all the reactions. Okay. So that's what this whole algorithm, the whole main RMG algorithm about this. Now, unfortunately, it's trying to reduce the model truncation error, but in order to do it, it has to estimate rates. But it's using whatever K's and K's we've got to estimate the rates. But some of those estimates are pretty lousy. So we're making decisions based on bad information. So therefore, sometimes we're not going to correctly select which species to add. And therefore, the model truncation error doesn't drop as fast as it should as we add species, because sometimes we're adding species which are useless instead of adding the really important one that we should have added. At the end, when you print out a model from RMG, very commonly you have significant parameter error because some of the K's are bad and some of the thermo is bad. And you also have significant model truncation error Because although RMG might say it's converged to some level, it might have mistakenly converged the wrong way, so it included some stuff that was not important and ignored some stuff that is important. So you're stuck in a bad situation because you have tangled up parameter error and model truncation error, and you're not sure what you should do. It's the normal situation. Okay. But definitely you have parameter error, because this whole procedure did nothing to alleviate parameter error. So let's do that next. So what you could do is build a model with RMG until it satisfies your termination criteria, which is basically your criteria that's related to model truncation error. Then do sensitivity analysis on that model and see what parameters in that model affect things you care about. And if there's some of those things you care about where you don't believe the numbers, the parameter values, then refine them. So you go do, say, a quantum calculation to get the very best number you can for the number you didn't trust that's important. And then you should update the estimation procedure so that the next time somebody encounters that exact same reaction, they won't get the same stupid number you had before, but they'll have your super duper fantastic number that you just did from all this hard work you're doing quantum calculations. Okay? And then you should go back and regenerate the whole model again. And now you get something different because you have some of the parameters are different. And so the model truncation procedure might actually build a different model for you. And if you keep doing this over and over until all the numbers that matter for anything are all great, then you think you have a great model and you're done. And you're ready to publish it and get the Nobel Prize. Okay? All right. So when you're working with RMG, you have to start from the beginning with the mindset that this whole thing is going to be iterative. Right? It's iterative inside RMG because it's looping around and adding species. And it's going to be iterative by you somehow, maybe externally, adjusting rate, refining rate parameters and thermo parameters to try to make it better. And then you're going to go back and do RMG again. And this whole thing is going to take a while. So don't promise your wife you're going to go to Hawaii the weekend because you might have to stay in lab and keep on working on getting your model better. Okay? So don't rush. All right. You're eventually going to be tightening up the tolerances. You're eventually going to be computing a lot of numbers. Eventually, you're going to get better numbers, and you'll be more and more close to the truth. And you're definitely going to keep improving feedback and refinements in RMG, so that RMG is going to cumulatively improve, and then everybody's going to be happier because we're all going to help each other by sharing our data and get better numbers. All right. So because you know it's going to be iterative, it's going to take a while, I highly advise you start simple. Make your tolerances not that tight. Just try to see, am I getting the main things roughly sort of semi-reasonable correct? Okay? And then go from there. Because you're going to have to keep going back and forth by getting the key parameters better. Then you're going to have to grow the model a little bit. Then you're going to have to pick up some other stuff. And you have to keep going back and forth. So start simple. And simple has an advantage of RMG will run faster. So your first few iterations, you can run it really quick. And also, you can check it much easier. The model's small. As a human, you can go through and look at stuff and figure things out pretty well. But later, towards the end, when your model's getting really gigantic, it's going to be really challenging for you to really comprehensively test if your model's any good. You know, once it has more than 8,000 species and 100,000 reactions, it's going to give you a headache, right? To even try to open the file might take a while on your computer, right? It's like so you want to spend some time in the beginning and make sure that at least the core and the main reactions and main species are really have good numbers and look very reasonable and everything's cool. And then at the end, if you happen to add some baloney stuff, in the last iteration, well, too bad you missed it, but at least all the main stuff was good. All right. So you usually know something about your system, more than you think, regardless of the system. And anything you do know, you can go and put them in. So you can put in as initial species in your input file. You can put in species you know are going to be important. That will help RMG to make sure it pays attention to them. You can use kind of a loose tolerance to begin with to make things run fast. You can check the molecules that it's generating and saying you're in the core and looking at them and saying, does this look reasonable to me that this would actually be a molecule I expect to have in my system? And if it's not, then you might be suspicious. Something's going wrong. You can check. And right away, almost right away, you'll realize, oh man, there's some numbers in this model which are totally baloney. I should better go start some quantum calculations, start getting better numbers for them, or start a literature search and see if somebody has a better number for that. So, you know, you can just start small and then kind of grow up. All right, so the key idea is you need to have expectations before you run RMG. And this is true for actually all modeling. So before you do anything on a computer, you always want to have, as a human brain says, I think it's going to be roughly like this. It's going to be like this big, you know, it's going to have, you know, my main product is going to be something or other. You have to have some idea. You typically have some idea what the time scale is. You might not know exactly what it is, but you know it's fast, or you know it's slow, right? So you have some idea. And often you have particular species that you demand that you will not accept any model that does not include these species, because I love these species, they must be in my model, okay? So if you know it, then demand it right away. Yeah, that's you have to assess it. And there might be some reactions that you expect to be in the model too. Another thing that's very challenging for people is to have a realistic view of accuracy. So in the literature, you'll see a lot of models that go directly through all the data points, okay? Remember, whenever you see that, almost always what that is somebody adjusted the model to make it go through the data points, right? They knew what the data points were, and they carefully adjust their model to make it go right through those data points, okay? That is not what you're doing when you're asking RMG to build a model. RMG is building a model. It's building its own estimate. It doesn't know anything about your experimental data, or anybody else's experimental data, basically. It's just trying to make an estimate of what's going to happen. So do not expect it to go through your data points. And do not get upset if it doesn't go through your data points. It's never going to go through your data points. So just get that out of your head. And the fact that you saw some dot-to-dot puzzles when you were a kid and you drew them in the crayon book has nothing to do with RMG at all. Okay? And it's worthwhile just to keep this in mind, that RMG energy estimates, especially barrier heights, are very often off by as much as 5 kcals per mole. Even the thermo can be off by 5 kcals per mole. And even if you do a pretty good quantum chemistry calculation, you could definitely be off by 2 kcals per mole. Okay, or if you get one from the literature. I mean, some people maybe you can do a little bit better than that, but it's pretty hard. So 2 kcals is not unusual. So definitely worthwhile to calculate 2 kcals per mole divided by RT, do the expectation at your temperature, and that's what you're entitled to. You are not entitled to anything that's more accurate than that. So this thing is going to be some factor, you know, like factor of 3 or a factor of 10, and that's what you're entitled to. And you should not be upset if you're off by that much, because that actually means perfect agreement. That's like you're within your error bar. That's what you expect. Okay. I think it's helpful to do that right from the beginning. So otherwise, you'll be tempted to try to do stuff to try to force the points. You know, the model to go to the points. It's very, it's a very unhealthy thing, actually. All right, converged. Very often, when we start to build models, we might use Hull of move to core, something like maybe 0.05, 0.02, 0.01, somewhere in that range. And that's perfectly fine to get the main pathways. But it's definitely not really converged at that level, typically. And typically, you'd have to go at least to like 10 to the minus 3, 10 to the minus 4, or maybe even lower than that, to really be converged in the sense that every single species that somebody might think is important in the system is really included in the model. If you don't do that, you'll find that some species are just left out. Now, the reason why we don't go there is the moment we set the tolerance that tight, it's going to take a long time to run RMG, and the model's going to be so big coming out, you're not even going to be able to analyze it because the model's going to be gigantic. It's going to put everything in there in the kitchen sink because it's trying to replicate everything that's in the real, lab test tube is supposed to be in your model. It could be a lot of species. What happens sometimes is you start to build a model, and it runs for a couple days, and you have a deadline, and you need a model, and it's not done yet, and you just sit like, stop, and you just take the model it's gotten so far, okay, and you use that. That's okay, but be aware, RMG did not agree with you taking that model out. You just stopped it. You killed that process and said, give me your model now. And it gave it to you. It said, I'm not done yet. I'm not done yet. I'm still working. You said, forget it. You're done. Here, come on. And it has a big certification on the top saying, RMG is saying, you have left out some important species or reactions. You definitely have. I have not converged. Okay? So just be aware, if you do that, your model should have on the top of it, this is an incomplete model. This is only some of the reactions that are important. All right. A really good clue, and easy for human eyes to see, is crazy species. So very often when something's going wrong in the model generation, some of the molecules in this model that come out look really weird. Okay? Most commonly, this is because a thermo estimator doesn't know how to estimate the thermo for that molecule, for that weird molecule correctly. And it's estimating it being too stable. And therefore, it thinks it's stable and it's putting in your output as a beta product or something. And when that happens, what you've got to do is we've got to fix RMG so it doesn't think that molecule's stable anymore, because as long as RMG thinks that molecule is stable, it is going to keep making that molecule, and it's going to keep showing up in your output tag. And not only you, it's everybody else in the universe that's using RMG is going to have exactly the same problem, but they're going to keep on getting that same stupid molecule. So when you find a case like this, first check what is the thermo that it's estimating for that. So you can just go into the RMG website, draw the molecule, ask it what the thermo is. It'll say it's negative 5 million kcals per mole. It's super stable. And then you'll say, well, that's ridiculous. It should be plus 300 kcals per mole. And so therefore, you have to check and see what was the source, how did it get to negative 5 million. And then oftentimes you can track down what the problem is. And then you might not know how to fix it, but you can definitely call Matt and say, hey, Matt, there's a problem. This species screwed up. I think the real number should be whatever. And Matt would be happy to add it to the list of training molecules, library molecules for the database, and then maybe later we'll be able to fix the estimation rule. And then after you fix it, rerun and check and make sure that the crazy model no longer appears in your model anymore, and then you're really happy. And sometimes you do this, and the same stupid thing keeps coming back, even though the thermo says it should not. And then probably the problem is a rate rule. So there's some reaction that's making this stuff, even though it's crazy. And then you can see, well, what were the reactions that made it? And you can look at the rate rules and see what, again, you can go estimate it from the website. You can see what exactly how it's estimating it. And then you can see, oh, the estimation rule doesn't know that nitrogen is different than sulfur, or whatever the heck the reason was, why it got the wrong number. And then you can go back to fix it. All right. And then again, if you find the problem in the rate rules, please let us know. And then we can go through a procedure to update it so that you won't keep getting this crazy thing, and also nobody else will get that crazy reaction anymore. Sometimes our model, and actually a lot of models in literature, include some unphysical rate coefficients. And RMG does a test at the end where it prints out a list of reactions that appear to be too fast, that appear to be faster than the collision limit. And you might say, well, how could this ever happen? And the way it normally happens is that somebody has a not too great estimate of a forward reaction and a really bad estimate of the thermo of the products. And then if you put those two together to get the rate in the reverse direction, then oftentimes it turn out to be faster than the collision limit, because the way the equilibrium constant comes into the reverse reaction calculation. So very commonly, this is another manifestation of crazy thermo, and it fixes the same way as you would for crazy species. If you think the thermo is right and it's still doing this, again, it'd be worthwhile to have a conversation with somebody in the RMG developers just to figure out what happened, because it's important to fix these things. All right, so now you have a model, and you think it's semi-reasonable. You don't have any crazy species that are really important, and you think you're okay. So now you want to check it. First thing you should focus on is selectivities. So is the model making the major products that you expect in anywhere close to the ratios you expect, like within orders of magnitude of the ratios you expect? And are all the major species you expected to show up showing up somewhere in the model? And are there things showing up as major species which seem nuts that they can't possibly be in a major species? And then you want to focus on trying to straighten that out to make sure that the model is more or less getting the right main channels to make the right main products. If you're missing a species, it could be that RMG did not pick up the reaction sequence that leads to that species. And this can be problems in the way that we grow the models. So it's a model truncation error kind of problem. And so look and see if the reaction sequence is there that you expected. If it didn't, then we'd have to analyze and figure out, well, why did RMG think that this was fast enough to matter to get into the model? It might just be, of course, that your tolerance wasn't tight enough. It could be that you have a bad rate parameter or a bad thermal parameter for one of the intermediates along the pathway that leads to that product. If you're picking up a species that you think is unreasonable for it to be there as a major species, often it's due to a bad thermo. Most commonly it's bad thermo. It could be a bad rate coefficient also. And again, you can go through and try to figure out which of the numbers is really screwed up that's leading to that product. You need to fix it. You can't just like pretend it's not there. So I've had some students like, la, 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 I won't look at my model, so therefore I don't know what kind of crap is in there. La, 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 I'm going to publish it now. La, la, la. Okay, this is a really bad strategy. If you have species in there that are coming up as major species, which are unreasonable, they're stealing the flux from your species that are supposed to be formed. As long as you leave them in there, you're never, ever, ever going to get the model to be right. You got to figure out why they're foolishly there, fix it, then they'll turn off. It's like closes that highway that's going to perdition and opens up this other pathway that's actually going to golden rainbows and stuff. Okay. Now, when you have a model that's like reasonable, where all the major species seem to be kind of reasonable, and there's no crazy species, in my experience, very often when you look at the selectivities there, they're actually very reasonable. And in fact, at high temperatures, very often we get predictions within a factor of 3 of the experimental numbers. We actually run like a GC and see what the products are. So you should be pretty good at this point if you've gotten rid of all the crazy stuff. It doesn't always work out that way, but if you do it, if you have some experimental selectivity data, like maybe you have a product yields at one condition, you run the model at that condition, and you look at the products, and oftentimes you'll be pleasantly pleased that you're actually producing the major products in maybe somewhere close to the proper ratios. And at that moment, you're like, the student who was doing la 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 is now like takes off the blinders and stops and looks at it like, oh, nirvana, I can publish my paper now. I have at least one plot, experimental data and model predictions, and they're actually like on the same page. Okay, the same plot, they all show up together. So that's really great. All right. If you can't figure out why your selectivities are wrong, it's extremely helpful to do sensitivity analysis. So sensitivity analysis for those species and see what parameters matter, and then systematically go through all of the top 10 parameters for each one of them and see where is the numbers coming from. And very commonly you'll find a rate coefficient that says average of average, or something like that. That's like RMG's secret code speak that means this is nonsense, don't believe this number. It also could be thermo, when you do sensitivities, it'll be sensitive to thermo. A lot of the important thermos will be actually correct because we spent a lot of time to make the thermo right, but you'll have, often one species shows up there, and where's the thermo coming from? It's some baloney. And then we just go correct that number, you might get a much better prediction. And sometimes you get stuff that just looks crazy. Like you might have a rate coefficient that looks like way too fast for whatever reaction it is. It is not unreasonable in that case, if you think it's completely crazy, to just make the rate coefficient 0, take it out of there. If you're semi-reasonable, but it's still not good enough for what you want, then it's worthwhile to do quantum calculations and try to get a good number. And definitely, thermo is usually the key. Definitely look at sensitivity to thermo. RMG can do it for you. Just get it. I know some coaches don't give you sensitivity to thermo. This is a big problem. Just make sure you look at the sensitivity to thermo, because our experience, thermo is by far controlling in a lot of systems. And if you get it wrong, you will never, ever, ever get the model right. And if you get it mostly right, even if your rate coefficients are wrong, you'll more or less get the right story. So the thermo is the thing we work on. And it's good because that's the thing we actually can calculate pretty well. So it's not that hard to deal with. All right. Now, after you finally have the selectivities that look semi-reasonable, then look at the conversion and the reaction time scale. And at this point, you'll be disappointed because RMG never gets the time scales for the conversion as good as you want it to be. And in many of the systems we do, pyrolysis, combustion, low temperature oxidations, it's controlled by free radical intermediates, but the free radicals are being formed by some chemical reactions and destroyed by some chemical reactions, and their steady state concentration is some kind of complicated balance between the formation and the destruction. And RMG has to estimate the formation rates correctly and the destruction rates correctly in order to get the steady state right. And RMG has a lot of trouble getting that right. So very often you're going to be off in these. And the general problem with this is that the RMG, the main RMG, the classical RMG selection algorithm is focused on fluxes, how fast reactions are. But the radicals are in quasi-steady state, so their rates are not, their concentrations aren't changing much, and the absolute rates of formation and destruction are all slow. And so often their fluxes are all negligible compared to the propagation reactions. And until you get 10,000 propagation reactions, you won't get any of these slow reactions that you need to get the radicals right. Now, you can try a lot of tricks, but I would say we have not yet hit upon the brilliant trick that works all the time for this problem. So one trick is you can try to just turn off the families except for the ones that change the number of radicals. So for example, recombination, disproportionation, they change the number of radicals. If you run the model and do that, you only allow it to add reactions of this type, and maybe with any luck, you'll get some of them that have high enough fluxes and they'll show in the model, and maybe it'll work out, right, to get it balanced out right. But this is a little problematic because after you add a bunch of strange new radicals, typically there won't be reaction paths for those strange new radicals to get back and connected with the rest of the system. Typically they have to be in a chain, a radical chain reaction, but some of the steps in the chain are missing. So in order to fill that in, you have to go back and add propagation reactions in. So you have to like go and iterate between adding radical reactions and then adding the propagation reactions and go back and forth. We should really write some kind of like script to just do this automatically. And then sometimes you're in bad luck that what's really happening is some kind of like autocatalytic chain branching process, and you need to have the entire chain branching process in the model before you get any radicals at all, basically. And that's a huge problem because until you have radicals, you have no reactions. But you don't have any reactions until you have all the, you don't have any radicals until you have all these reactions in. So it's like a chicken and egg problem. And this is a big problem. And Matt's worked a lot of trying to figure out ways to do this, but I would say this is still a work in progress to make this really good. If you find a case where your selectivities are fine and your conversion is just way off, or your ignition time or something like that is off, talk to us about it, because we've been looking for good cases to really focus on and test out all our different ideas of different algorithms to try to help get the conversion better. Now, you will be tempted to try to tweak some parameters and force your model to go through the points. Okay, you learned that in nursery school how to do dot to dot, and you want it to work, and you'll be highly tempted. I have to tell you, it is not recommended, but I know you're going to do it anyway. I'm an old guy. I've seen it all. So I have to say what parents say to their children: be good, but if you can't be good, be careful. If you're going to tweak the model parameters, be really careful what you're doing and pay attention to what you're doing, and honestly represent, when you write papers about it, what you did. Because there's so many ways you can delude yourself and even worse, delude your readers of your arguments about what the truth is, unless you do this carefully. Just be aware that in these big models, you will never have enough data to determine all the parameters. So you are highly dependent on the estimates of the parameters because you cannot determine them from the experiment. And often you can find some parameters that if you tweak them the right way will make all your curves go through the points, but typically that will not be a unique solution. Typically it will be a whole bunch of different possible combinations of tweaks that would work right to match your limited data. And so it's easy to delude yourself that this model is now true because I tweaked, parameter 17. But how do you know that 17 was the one you should have tweaked? Maybe it was 19 and 21 together or something, and it would have worked out just the You can also, it's very helpful to combine sensitivities with estimates of uncertainties. So roughly speaking, the uncertainty in an observable should be something like the sum of the sensitivity of observables times the uncertainties in the observables. So this is like d ln of my observable, d ln of a rate coefficient times uncertainty in the logarithm of the rate coefficient. And that term is how much the uncertainty in this rate coefficient is contributing to the total uncertainty of the observable. This is all assuming the first order sensitivities. So if you do this, this gives you like a realistic idea of like what accuracy you're entitled to and what you think. And then also you can see which of the terms in the sum are big, and those are the ones that the parameters really matter, and where you might want to narrow the uncertainty of the parameter value. So this is a very helpful thing to do. And this whole thing, of course, though, is only about parameter uncertainty, and it does nothing to fix your model truncation error. So this is all about parameter error. So all the time, you'll start fixating on one or the other. Like as you're running RMG, you're always fixating on model truncation error. Where did the other reaction come from? Where's the other species coming from? And you forget about the parameter error. Then you have to go spend 3 weeks doing quantum calculations, and you get all that, worry all about parameter errors, and you forgot, oh, well, actually, I'm not really sure my model's that good. You have to go back and forth between the two to really get this straight. That's all I have. I don't know if other people have suggestions or comments about practical advice.
So something, I probably should have said this in the RMG run lecture, but tolerance is can be very, very relative. If you have, I think Colin had some models where it had to be set drastically lower just to get the kind of results, what I would expect from setting like 0.1, just to get that, he had to put like 1E5, -1E -5 or something. So the tolerance is more of a dial that you turn up and down to add more stuff to your model than a converged model at 1E4 versus a converged model at 1E -3 is a little bit.
Yeah, and the effect of the tolerance is different at different stages. So when you don't have many of the key reactions in, it's really unpredictable what RMG will do, because you have a fractional model that's like unphysically forgetting a lot of stuff, and its estimates of all the rates will often be really screwed up, and therefore it's like its whole behavior would be really weird. Whereas later, after you have a really full model that has almost everything in it, then things start to act like much more normal, like you expect. Like you just tighten the tolerance a little bit, you get a little bit more stuff. It's all like makes sense. In the beginning, you have very erratic behavior, and it might depend exactly the conditions. So yeah, be patient. Be patient with yourselves. It's going to take a while to get to the point you have almost everything that's important included. At that point, the regular RMG algorithm starts to work a lot better. Yeah.
Maybe you already said it, but if you update your model and you find from literature or calculate a nice rate, make sure you add it as a training reaction, so other rates will benefit as well, not only that particular rate you calculated, and donate that knowledge to RMG, become a contributor to the project.
Yeah, and I think, is this right? Although you added a training reaction then, it will not immediately change the estimates in your model. You actually have to ping Matt and say, hey Matt, I just added some really great training reactions. Can you please rerun the estimator? Is this correct?
Well, okay. So the tree training isn't implemented. I mean, I can do it for trees, but we aren't doing it for all the trees yet.
It's definitely not routine.
For now, you have to go in and add your own nodes yourself inside the tree.
Anyway, so if you it's very, like emphasize what Alon said, it's extremely important that we all contribute our good numbers. It's the only way that this will ever get better. However, don't expect the moment you put it in that immediately everything will be solved. But if you're urgent to get it to reflect it in what happens in your model, you communicate, say, with Matt and say, hey, this would be, what should I do? And then maybe Matt can give you advice about how to pass it to use your training reaction to make sure that it affects a big block of your code and not just the one reaction. And similar with thermo too, right? Thermo's not automatic either.
Thermos. So I mean, adding it to the machine learning algorithm, I think would be easy theoretically. If Colin.
But right now, if you just download it, it will not automatically update.
I mean, adding it to a thermal library is super easy, but improving group additivity is more complicated, much more complicated.
Yeah. So both those, in principle, it can do it, and we've done it, but it's not enabled on your copy of RMG. It's not going to automatically update the estimates unless you talk to us.